Now we'll talk about expansion of bounded lengths. When we talk about bounded lengths are those dimensions which are bounded by a single material, like say we are given with a disc which is made up of copper, and if we draw any line on it, say a line between 2 points A and B, so both points A and B are located on the same material, so this length is bounded by the material copper only. There is no other material involved in it. Say if its length is L1 and the disc has a radius R1. So R1 is the distance from center of disc to its periphery. In this situation, if we increase the temperature of this disc from T1 to T2, obviously on increasing temperature, the size of disc will increase certainly. In this situation, if the size is increased, obviously the radius of disc will also increase from R1 to R2, and the separation between points A and B will also increase from L1 to L2. In this situation, as the material is same as copper and if its temperature is increased from T1 to T2, we can see that all the lengths or lines drawn which are between the points joined by the same material, we can use the direct relation of linear expansion over here, like in this case we can use L2 is equals to L1 multiplied by 1 plus alpha of copper into delta T. Similarly, we can use R2 is equals to R1 into 1 plus alpha of copper into delta T. Or any other length, the same relation can be used for circumference, diameter, or any other lengths also we can use. So be careful about any kind of bounded lengths. For bounded lengths, let's have one more example for the same. Let's discuss one similar application on bounded length expansion, like say if we are having a half ring. In this situation, say this is the center of this half ring, and on the ring we consider 2 points X and Y which are at a separation L1. You can see that L1 is the length in air, but the points X and Y are connected by the same material of which the half ring is made up of. So this half ring is made up of aluminium. So we can directly use for expansion of this length by using the coefficient of expansion for aluminium. Say if this is a temperature T1 and if we increase the temperature to T2 such that delta T is equals to T2 minus T1, obviously the dimension of this half ring will increase, and in this situation all the dimensions associated with it also increases. This is the center, this is aluminium only, and say this is the X point, this is Y point. So for the line joining X and Y, if the length changes to L2, we can directly use L2 is equals to L1 multiplied by 1 plus alpha of aluminium into delta T. This is the relation we use because this length is bounded by the same material aluminium. And similarly, the expression is valid for superficial expansion also, like say if we join the two ends of the half ring and if we talk about this area, which is obviously if the radius is R1, then its area will be pi R1 square by 2. If say this area is A1, and after expansion if its radius is R2, then this area changes to A2. We can also write A2 is equals to A1 multiplied by 1 plus beta delta T or 2 alpha of aluminium delta T. This is the relation we can use also. Or similarly, this linear expansion result is valid for expansion radius also, because the center of ring is fixed, the ring is expanding. Or even if it is not fixed, we can apply this result on radius, because the material of this half ring is aluminium and it is expanding uniformly in all directions. Now we'll talk about expansion of cavities. The concept is similar to the expansion of bounded lengths and area, which just now we have discussed. Say, and to understand this expansion of cavities, we consider a solid sphere in which we have created a cavity. The sphere, let us consider it is of radius r1 and the cavity we have made is of radius r2. And say we talk about the volume of this cavity, its volume we can consider to be Vc. Say this right now at temperature T1, and if we increase its temperature to T2 such that delta T is T2 minus T1, then obviously all the particles in this material of which the sphere is made up of will expand. So the whole sphere will expand like this, due to which we can say the cavity will also expand. However, it gives sometimes a weak feeling that if the material will expand inward, the cavity may contract, but practically it is not possible, because if the material will expand inward, the separation between the particles of material will decrease. Whereas we have studied that due to rise in temperature, always the separation between particle increases, so expansion always takes place in outward direction. So this changes to R2 dash and the radius of this sphere changes to R1 dash. And if coefficient of expansion for the material of the sphere is alpha, then the relation we can use R1 dash is equals to R1 1 plus alpha delta T. Even for cavity it is filled with air, this is the radius of air bubble only. Even after that we can use the same relation because it is bounded by the same material. So we can write R2 dash is equals to R2 1 plus alpha delta T, as well as we can use the relation for its volume. So its volume finally will change to Vc dash. So we can write Vc dash is equals to Vc into 1 plus gamma delta T, and here gamma is the coefficient of cubical expansion, which can be written as 3 alpha for solids.